I changed a bit the title of my presentation. That's because when we submitted the abstract, we thought that we could solve this problem by employing only a machine learning approach, like a purely based on a machine learning approach to predict fatigue life, finite fatigue life in additive manufacturing techniques, materials. So after a while, then we realized that that was not possible simply because if you want to use a machine learning approach, you need to know and to have a lot of data, which is rather unusual to get data, a lot of data in fatigue problems. So we attempt this to propose this new method based on physics-informed machine learning, where we try to combine something from semi-empirical modeling and the machine learning approach. Okay, so the content of my presentation is basically, I'm going to introduce briefly the role of defects, which has been already presented by Alessandro this morning in his plenary lecture. And then I'm going to show you some modeling approaches based on semi-empirical linear electromechanics and also machine learning approaches. Then I'm going to present my new hybrid approach, and then a case study from data taken from literature. And I'm going to draw some conclusion and give you some insight for future development. Okay, let's talk about the role of defects in fatigue. Defects are always present in materials, and because they are due to manufacturing process, and they can be thought as porosity, inclusion, etc. So we know that for emerging manufacturing processes, it's very common to have defects because they're not mature enough to have like a fully homogeneous material. So one case is additive manufacturing. We can see from the figure here, from a CT scan, we have a map of defects, pores, and then we can see a fatigue sample, so the fractography of a sample subjected to fatigue, and the crack propagation creation site, which is actually at a lack of fusion porosity. We can also see from literature that the influence of porosities in particular is very strong as concerns the fatigue property of these materials, and we can also see that if we apply some thermomechanical treatments to these manufactured materials, we can actually improve a lot the performance. For example, if we apply this heap process, so basically we close all the pores, we can improve the fatigue properties 2, 3, 4 times, even 4 times. Okay. Obviously, for practical application, if we deal with the real components, it's not obvious, it's not always doable. We cannot post-process all the components. So we need to develop a model that can account for the defect population of materials, and then we need to live with that. Okay, predictive modeling, I can refer to linear elastic fracture mechanics, which works well for high cycle fatigue, but there are many others which can account also for low cycle fatigue, resin. Basically, linear elastic fracture mechanics, as you all know, refer to stress intensity factor calculation range in this case because we're dealing with fatigue, and we rely on the approach proposed by Murakami so that we analyze each defect and we analyze the square root of the area in the plane normal to the loading direction. Okay. And then we need to calculate the stress intensity factor range. We need to account also for Y effective, which is basically a factor that accounts for the position of the defect and its dimension. Okay, so we have 3 regimes. Obviously, if the pore is small with respect to the sample and is far away from the surface, it has no effect. So the distance from the surface doesn't have any effect. So this YF becomes 0.5. How can we transfer this information to predict fatigue life? lately there have been proposed that few approaches. One of them is like by correlating the stress intensity factor range with the fatigue life, so we consider the stress intensity factor range as the fatigue driving force. We're going to employ this into this presentation. On the other hand, if we employ machine learning has been employed very lately. So I'm talking about 1 or 2 years. Okay, so one of the few works on this employs support vector regression. So there are samples which have been analyzed through computed tomography. So we have all the statistical information of all the porosities, and then they tested under fatigue conditions, and they try to make prediction. This is pure machine learning. There's no information about physics or any other phenomenological things that we know beforehand. Another interesting work that we can see, we have seen in the literature, is that again they use machine learning. With pure machine learning, they try to understand what is the influence of each morphological feature of the defects. And we can see that if we consider 2 different batches, so manufactured with 2 different manufacturing processes, the influence of each feature is it's different, right? So in one case, for example, I was talking before about the distance from the surface of each defect. Here in batch 1, the influence is very low. In batch 2, is very high. So how is that possible? It all depends on the presence of the defect, when the presence is, where the defect is, or where is the morphology of the defect is, if it is a lack of fusion, if it's a pore gas defect, and so on. So that means that not always we can employ fraction mechanics to solve this problem. That's why we need somehow to combine. So which approach should I use? Machine learning or fraction mechanics? It all depends, as I briefly told you, depends on the data set. Okay, so we need to rank before the data set size. So we say if we have the small data, okay, we don't have any options. The only option is linear fraction mechanics or other semi-empirical models. On the other hand, if we have like a big data set, we can rely entirely on machine learning. Okay. But what about a more realistic scenario? We have some data, right? So certainly we can use linear elastic fraction mechanics, but maybe we can exploit some potentials of the machine learning, right? So the solution and the approach that I propose here is essentially physics-informed machine learning. Physics-informed machine learning is now I refer to a neural network, but can be extended to other type of machine learning. Basically, we provide some inputs that is black box, I would say, and then we get an output. This output must be correlated to the actual value, so the value that we experience experimentally. And the peculiarity of the physics-informed neural network is that we apply a further constraint to the model, which is essentially this function that tells you that, look, this is your prediction, but this prediction must obey a certain law. Okay, it's a law that comes from phenomenological models or semi-empirical. Let's try to understand what is the condition that we need to apply into this neural network. Let's say we have a set of experimental data. Okay, from CT scan, we can get. This is the physics model. So from CT scan, we can get all the interesting information we need. So the square root of area according to Murakami, the distance from surface. Then we fatigue the samples, and we have the applied load and the number of cycles to failure. And if possible, we can get also some information about the actual killer or killer defect through factography. And then from that, we can actually put everything into analogously like a S and curve. This is stress intensity factor range versus logarithmic versus the number of cycles. But we decided to normalize the stress intensity factor by the stress intensity factor threshold, because we know that for short cracks, as Murakami has shown, the stress intensity factor threshold changes if the effect size changes. So we're going to show you later that this is quite effective. Then we fit everything with the basking-like curve, so it's a power law. And we decided to select the first three defects if we only rely on CT scan. Okay. We decided to have it only the first defect, the first highest, the defects that show the three highest normalized stress intensity factor to construct this curve. Okay, and we obviously define this prediction one. Okay, and then what about the neural network, so the machine learning part? We try to introduce other parameters that can have an influence into the fatigue life, such as the equivalent diameter and the sphericity. So we put everything into this neural network. Obviously, the layout of the neural network must be like thought. It's not that straightforward. So we put everything as an input, and as output we decide to have obviously the number of cycles. So what do we do now? How do we combine the semi-empirical and the neural network? This is the semi-empirical model. For each, so this input refers to each defect. So each defect has a certain morphology, and the sample is applied, is subjected to this load. So for each defect, we can actually calculate the normalized stress intensity factor. We enter this curve, right? And then from that, we can get an estimate of the maximum number of cycles and the minimum number of cycles. So we know that our predicted life must lie within this region. Okay, we don't want an exact number. We don't want to match exactly the number of cycles. Okay, that's because this is a model based on defects, but we know that it's not only defect that plays a role. There are residual stress, anisotropy, unhomogeneities related to motor structure, and so on. So the only constriction is that it must lie in this scatter band. So we force that, we add this to the loss, and we get, then we run our model. The validation is done through an experimental data set provided by Romano and Beretta. They provided us 12 samples. They've done CT scans. They loaded at under fatigue at -1, and they provided also sphericity at the equivalent diameter. So first of all, we evaluated whether the normalized stress intensity factor was effective, and we realized that it was actually effective. So it gives a narrower scatter band, so it can be employed. And then we did the actual prediction. So out of 12 samples, we used 10 samples to train the machine learning, the physics informed machine learning, and we used 2 samples just to verify. It was a test sample. Okay. So, and then we did also a key-fold test. So we did some permutation of these 2 and 10 samples to actually assess the robustness of the method. So these are just 2 examples, but we did many. So if we focus a bit more, we can see that we don't have exact matching as we expected. For example, these are experimental, this evaluation, so the rounded are experimental. We don't have exact matching, which is acceptable. And if we focus on the prediction, so on the actually the tests, the 2 samples, we can see that we have quite a good agreement. So I go to the conclusions. So we have shown how physics-informed machine learning technique can overcome some limitation of purely machine learning-based approaches. So we have proposed a semi-empirical model, and then we can also account for several other influencing factors that cannot be accounted for in linear isotopic mechanics. And it is robust, and it's flexible, so we can also add some more data. I just showed you how to employ the sphericity, the equivalent diameter, but we can have more morphology features. And for future works, we would like to extend the validity of this model to other fatigue regime. For example, we would like to estimate fatigue limit if it exists, or for instance, low cycle fatigue and other things. So some acknowledgements, and thank you for your attention.
Thank you so much. We have time for one question because we are very close to the lunch time. Yes?
Thank you for your presentation. I'm just curious, how do you define small data set and some data in your area of research?
Well, we know
What
that
is for you some data set?
some data set is like, we're talking about at least like tens of data, tens of samples. If we talk about like few samples, let's say 1, 2, 3 samples, that's not enough. We cannot even construct a machine learning starting from that.
So tens of data, not
Tens.
hundreds.
Not hundreds. No. I mean, hundreds. Yeah, you could do. Yeah, in principle, yes, it would work well if we had like you know, the capability to do CT scans for 100 samples and then do all the tests. It was a real struggle to find some experimental results available in the literature. We would like to do some our own experiments, but we know that these experimental results are very valuable. Yeah, that's the word.
I understand the struggle, so that's why.
Yeah, okay, we are on the same line now.
Thank you so much, Enrico.
Okay.